Hello friends, welcome to the lecture series on engineering graphics. I am Dr. Shivraj Narayan, Professor of Mechanical Engineering, VNR VJEC. Our today's session is mainly focused on the construction of cycloidal curves. In this session, you will be learning about the concept of cycloidal curves and how they are generated by a rolling motion. The next important thing that we are going to learn is about the method of construction of cycloidal curves using AutoCAD software. So before we delve into the construction of cycloidal curves, we should understand what exactly is the cycloidal curve. So as shown in this slide, a cycloidal curve is nothing but a curve generated by a fixed point on the circumference of a circle which rolls without slipping along a fixed straight line or a circle. And that is quite evident from this animation. You are able to see a circle which is continuously rolling along a straight line. So what has been done? We have taken one common point on the circumference of circle, and the path of this point is being traced when it starts rolling on this straight line. So this rolling can happen for specific distance. So when we make the circle to roll for one complete revolution, then the distance that is covered is equal to circumference of circle, which is 2 pi r, which is shown over here. So at the end of one turn, this point P will complete one full travel, and the path that is generated is generally called as a cycloid curve. So why do we have to learn about these cycloidal curves? Because these curves, they are used in the design of gear tooth profiles as well as in the gear mechanisms. Now coming to the types and terminology of the cycloidal curves, we basically have three types of cycloids. One is the cycloid curve, the second one is the epicycloid, and the third one is the hypocycloid. Now when do we call a cycloidal curve as a cycloid curve? So the condition is given over here that the circle should roll on a straight line. So here this circle, the one that is shown in the dotted line, is basically a rolling circle or a generating circle. The name of this circle is rolling circle or a generating circle, and on this circle we take one point P whose path we want to trace. So when this circle starts rolling on a fixed straight line, then the path that is obtained is generally a cycloid curve. So what we have to remember is we get a cycloid when the smaller circle, the rolling circle, rolls on a straight line. So the terminology is being shown over here. The circle that rolls is called as the rolling circle or generating circle. Then this is the fixed straight line, which is also called as the directing line, and the path that is generated, that is called as a cycloid curve. So how much distance this circle will travel for one complete revolution? So that you have to remember, in the case of cycloid curve, the distance covered will be equal to circumferential length, which is 2 pi r. Then the next type of cycloid is the epicycloid. So here in the first case we saw that the rolling circle is rolling on a fixed straight line. Now what if the circle starts rolling on another circle? So we get two possibilities. The smaller circle can roll on another circle but outside it, and the third one is the last type of the cycloid curve. The smaller circle can roll on another circle but inside it. So whenever the smaller circle, the rolling circle, rolls on another circle but outside it, as shown over here, when it is rolling on another circle but outside it, then the path that is traced is called as the epicycloid curve. And when the smaller circle, this is the smaller circle, and when this smaller circle rolls inside a bigger circle, then the path that is traced is called as a hypocycloid. So we have these three types of cycloidal curves. One is cycloid, wherein the circle rolls on a fixed straight line. Then we have epicycloid, wherein the rolling circle rolls on another circle but outside it. And the third type is hypocycloid, wherein the rolling circle rolls on another circle but inside it. Now we have already specified for cycloid curve that for one complete revolution of the rolling circle, the distance traveled will be equal to circumferential length. Now what happens in the case of epicycloid and hypocycloid? Here also the smaller circle, the rolling circle, will be starting at one point and it will move on to another point until it completes the one revolution. So it will not be able to cover the entire circumference of circle. It can only complete partial section. So that distance, if you want to find out, then we need to calculate angle. And that is given over here. The angle covered in by the rolling circle in one revolution is equal to, the angle notation is theta, and it is given by 360 degrees into small r by capital R. Now what is this small r? Small r is the radius of this rolling circle. Rolling circle is the smaller circle which is going to roll. So small r is the radius of the rolling circle, whereas capital R is the radius of the fixed circle or the directing circle. The circle on which the rolling circle is going to roll is called as the fixed circle or the directing circle, and its radius is denoted by capital R. So if we are able to solve this, we'll be able to get an angle, and that angle basically helps us in telling how much portion of the circle has been covered by this rolling circle in one complete revolution. Let us now move towards the problem. So this is the given data. A circle of radius 25 mm rolls on a fixed straight line in the first case. In the second case, it rolls on inside a fixed circle of radius 60 mm, and in the third case it rolls outside a fixed circle of radius 60 mm without slipping. We have been asked to draw the curves traced out by a point P on the circumference of the circle for one complete revolution, and for each one of the case we have been asked to name the curve. At the end, we have been asked to draw a tangent as well as normal to each of the curves at a point. For the first case, it is 40 mm from the baseline. For the second case, it is 95 mm from the center of fixed circle. And in the third case, it is 40 mm from the center of the fixed circle. So it is basically a common problem statement wherein three different cases have been defined. Now let us see how to construct the cycloid curve first in AutoCAD. So let us move to the demonstration. So first of all, I will write the given data. So I'll make use of mtext command. So we have been given rolling circle whose radius is radius of rolling circle, which is nothing but small r, as 25 mm. Then it is rolling on a fixed straight line, and the number of revolutions are given as 1. So with this data, we are supposed to draw the cycloid curve. So before we move to the construction, the very first thing that we need to do is we need to find out the distance that will be traveled by this rolling circle for one complete revolution. And that distance is equal to circumference of circle. So length PA is equal to distance traveled by rolling circle in one complete revolution. And this is equal to 2 pi r. So 2 into pi into small r. So we can find out this value. So how do we find out? You can make use of calculator in the AutoCAD software. So simply type CALC and press enter. You'll be able to get this box for the calculator, and now do the calculation. 2 into pi into small r is 25. So the value is 157.079, which is nothing but 08. So I'll write down 157.08. So this is the distance that will be traveled by the rolling circle in one complete revolution. Now we need to draw the cycloid curve. So the very first step is to draw the given rolling circle of radius 25 mm. So make use of circle command, define the center and the radius as 25 mm. Next, we need to locate the point P on the circumference of circle. So that is the point P whose path we are going to trace. Now in order to do that, I am making use of line command, and I am drawing a line from the center of circle you can make ortho on so that you get perfectly vertical line, and this line should end exactly on the circumference. So what I'm doing is I'm going to the OSNAP features and I'm making quadrant on. Now move the cursor over to the circumference of circle, then the software will show you the quadrant point. So click on this. So you got a line, and now wherever we have clicked, that is the point P whose path we are going to trace. From here we need to now draw a line which we call it as fixed line. So this fixed line is the line on which this rolling circle is going to roll. And the distance of this line we have already calculated, it is 157.08. So keep this as horizontal and type 157.08 as the distance. Next, we need to divide this circle into some number of equal parts. Now in order to do that, what I'll do is I'll make use of array command. So type array. It is asking to select the object, so I'll make use of this line for array. So select this line, press enter. Now it is asking whether we want to go with a rectangular array or polar array, so click on polar. Then it is asking specify center point. So now pick the center point of circle as the center point of array. So by default it is now showing me the polar array, and the default value is 6. So that's why it has now divided the circle into 6 parts. So generally we do it for 12 parts, but here I will show it for 8 parts. So now how to change this 6 divisions into 8 divisions? So we have one of the option called as items. Click on these items, and you can see in the square bracket, the curly brackets, it is written as 6. Now simply type 8 and press enter. You can see the change in the division on the circle. Now we have got 8 such lines. So we have divided the rolling circle into 8 parts. Now whatever number of parts we have divided the circle into, the same number of divisions we need to make it on this line. So for this, now I'll make use of a command called as divide. So I'm typing div, press enter, select the horizontal line, type the number of segments as 8 and press enter. So you can see the line has been divided into 8 parts. Now before we proceed further, I'll write down the names and numbers on these points so that we'll have clarity. So for that purpose, we'll make use of mtext command. So I'll designate this as point C, center of circle. I'll copy this text, make ortho of, place it here so as to indicate that this is point P, and then you can show this as 1, 2 and so on. So for that we are placing the text at these locations. Similarly, we have the divisions on the circle. So here also we can place the text. Then double click and edit it to the correct names. So this is point P whose path we are going to trace. Then this is 1. Similarly 2, 3, this is 4, 5, 6, 7, and this point P itself is the 8th point. So you can also show this as 8 and P. Similarly on the lines, we will now number it as 1 dash, this is 2 dash, similarly 3 dash, 4 dash and so on. So write the number names at each one of the division points. So once we have completed this, now the next step is we need to draw the locus or the path of these division points. That means through each one of these points on the circle, 1, 2, 3, 4 and so on, we need to draw locus lines. So these locus lines will be parallel to the line PA, that is the fixed line or the directing line. So either you can make use of copy command or you can make use of offset command. I'll show both. So I'm making use of copy. I'm picking the line PA, press enter, select the endpoint of the line P, and then you can place it at either point 1 or 7. So like this you can make use of copy command. Similarly, you can make use of offset command. So I'm typing offset O, and now click on through option. Don't specify any distance, but instead you can click on through option. Select the line to offset. The object to offset is nothing but this line. So select this line and then place it at the required location. Again, you can select the line and place it at the required location. So like this you can do it. Either copy or offset command can be used. Now you can see on the right side, these lines are not correctly ending at the endpoint A. So for that purpose, you can draw a vertical line, join it with the topmost line, and then make use of extend command. Next, what we need to do is through each one of these division points on the fixed line PA, that is 1 dash, 2 dash, 3 dash and so on, from each one of these points we need to draw perpendicular lines. Now why are we doing that? Because we want to find out the locus of center and where will be the center point located once the circle starts rolling. So what I'll do is I'll make use of line command, click on 1 dash and draw a perpendicular line or vertical line up to the line passing through center C. So wherever this line is touching or intersecting the line passing through C, that is the position we call it as center C1. That means when one division distance is traveled by the circle, this center C will now move to new center point C1. Similarly, as the circle progresses further, the same circle center point C1 will now move to C2. When it moves further by one more division distance, the center C2 will be at C3. So in order to find out those C2, C3, C4 and so on, what we need to do is we need to draw lines which are perpendicular from 2 dash, 3 dash and so on. Now once we have drawn this 1 dash line, what you can do is you can copy this or offset it as per your wish. Select this line, press enter, pick the end point of the line and go on placing it at 2 dash, 3 dash, 4 dash, 5 dash, 6 dash, 7 dash, and already there is a line at 8 dash. Now wherever these perpendicular lines are touching or intersecting the line through C, they are new center points. So I'll make use of copy command and I'll place the text over here, C1, C2, C3 and so on. We need to name these points. Double click and update the names. So one by one, you need to double click on this, type the number and update it. Now once you have correctly numbered this is the initial construction part, so which we have completed. Now we need to trace the locus of point P. So what we do is we start assuming that this circle starts rolling, and when it starts rolling, so there will be two motions involved. One is linear and another one is rotation. So that means this circle will start rolling and it will try to reach this endpoint A position. Now in order to achieve that path P, what we do is we assume that the circle starts rolling by divisions. That means whatever divisions we have created, we need to make use of that data. So we'll assume that the circle rolls by a distance equal to 1 division. So that distance is nothing but P to 1 dash. So when the circle rolls by a distance equal to 1 division, what happens is the center point C, it also gets displaced and it moves to a new location C1. Now what we know that the distance of point P from center C is fixed, and that is nothing but equal to radius of rolling circle. So if now my center of circle is at C1, I know that point P has to be at a distance equal to radius of rolling circle. So with that logic, we start constructing the path of the point P. So in order to do that, what I'll do is I'll copy this circle, press enter, pick the center point of circle as the base point, and now place it at C1. So now you can see, when we assume that the circle has rolled by 1 division distance, this will no more be existing. The circle would be something like this. It has traveled by a distance equal to 1 division. So when it is traveling by a distance equal to 1 division, now we need to find out the position of point P. So where will be the position of point P? So it will obviously be on the locus that is passing through division point 1. So point P has to lie on this locus of 1. And what we know that the distance of point P from center is nothing but radius of circle. So from C1, we take this C1 as center, smaller as radius, we draw an arc on locus of 1. Now instead of doing this entire procedure of drawing arc, I can make use of the same circle and achieve the same point. So what I have done is I have placed this circle on this position, C1 center position, and I know that my point P has to lie on this line number 1. So now I'll make use of break command, and this is the line and this is the circle. I know that the intersection of line and this circle will give me a point, and the distance of this point from C1 is 25 mm. So it justifies our requirement. So I have gone to the break command. I am clicking on this circle on the bottom side and now moving upwards. So I got the same effect as that of drawing arc. I use the circle which was copied. Instead of going to an arc command and doing the procedure, I made use of the copied circle. And if you now check the distance of this arc from center, it will obviously the radius of rolling circle. Now we need to repeat this process for each one of the centers. That means now we assume that the circle has rolled by one more division distance. So when it happens, this C1 the circle which is now at C1 position, center position, it will now move to C2 position. And in order to visualize this, we will copy the circle again, press enter, pick center point of the circle as the base point and place it at C2. So after 2 divisions rolling, the circle will be somewhere here, and I know that point P has to be at a distance equal to radius of rolling circle, and that point P has to lie on now locus number 2. So we can see this locus number 2 is here and this is the circle. So both are intersecting at this point. So this is our point on the cycloid curve. Now in order to show that in the graphical form, we'll make use of break command. Type BR, press enter, click a point on the circle on the downside and move upwards. So you got another arc. Repeat the same procedure now. Copy the circle, press enter, pick the center point and place it at C3. So when the circle travels by a distance equal to 3 divisions, so says center will be at C3, and obviously the point P will be on locus of division number 3. So we can see this is locus of 3 and this is the circle. So the intersection point is the point on the cycloid curve. So make use of break command, click on the circle on the downside of the line and move upwards. Now exactly at the 4th division what happens, we know that we have divided the circle into 8 parts. So half of it is 4. So this fourth division, it indicates the half distance. So the point P, which was exactly at the downside, at the fourth division, it will move to the topmost point. So for the fourth point, you need not do the entire construction. You can simply make use of extend command. Now what we have done, we have constructed 3 arcs, and the midpoint, we are saying that the middle of this line, it will be the half distance. So we know that the cycloid curves, they are symmetrical curves. That means the shape on the right side and the left side will be symmetrical or same. So by making use of this property, what we do is, we will not repeat the construction now, but instead we will make use of mirror command. So pick these 3 arcs, press enter. Now it is asking specify first point on mirror line. So pick the end point of the line which is starting from 4 dash, and pick the other endpoint of the same line. Then it is asking erase source objects, specify no. And you can see on the other side also we have got the remaining 3 arcs. Now you can make use of spline command for joining all of these points. The spline command, you should start drawing from this endpoint P. Many students, they will start directly drawing it from this first arc point. But you should remember that we are tracing the path of this point P. So the curve should always start from P. Then pick this first point, next point, next point, next, next, and the last one. Now once you have picked all the points, click on this end tangency option and just look for the correct shape of the cycloid curve. Wherever you are able to visualize the correct shape, you click on the screen. And you can see you already constructed the cycloid curve. Now select this curve, right click, go to properties, change its color, increase the line weight, 0.35 or 0.4 you can keep. So we need to do this because we need to show that this curve is our final answer. We are saying that this curve is our final outline or answer. Now what else is remaining over here is we need to show the points on the cycloid curve. So make use of any of the available text. So I'm making use of the C1. Select this, place it at this location, next, 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 and similarly the remaining ones. Double click and give the correct names. So this is P1, this is P2, next P3, P4, then P5, P6, P7, and the last one is P8. So this is the cycloid curve. Next, we have been asked to draw a tangent and normal, and the distance is given as 40 mm from the fixed straight line. So the fixed straight line is nothing but this horizontal line PA. So from this, we need to draw a line which is at a distance of 40 mm. So that line is going to cut the cycloid curve at some positions. We need to pick one of the position and then draw the tangent and normal. So in order to locate the position of the point at which we want to draw the tangent and normal, we'll make use of offset command. So type O and press enter. define the distance as 40 mm, select this line and place it on the top side. Now here, if you can observe, I have selected this line. The line is cutting the cycloid curve at 2 points. So you can pick any one of the points as the point where you want to draw the tangent and normal. So generally we prefer the right side point, because on the left side already there is a construction of circle, whereas the right side is literally free. So we'll pick this as the point and we'll call this as point X. So what is this X? This is the point where we want to draw the tangent and normal. Now take this X as center, radius of rolling circle which is 25 mm as the distance, draw an arc on the locus of center. So you can make use of arc command, go to center option, pick this X as center, type 25 mm as radius, press tab key and then draw an arc. So what we have done, we have taken X as center, radius of rolling circle that is 25 mm as radius, and we have drawn an arc on the locus of center. So this arc is cutting the locus of center at some point. So now from this point, draw a line which is perpendicular to the fixed straight line P. So from X we have drawn an arc. Wherever the arc is cutting the locus of center, from there we have drawn a perpendicular line to P. Wherever this line cuts the line P, that is our point N. Now join N with X. You can see the angle is 63. Maintain that 63 angle and continue the line. So this line is the normal line. So I'll copy this N point and place it here. Double click it and change it to M. So this line is normal, and a line which is perpendicular to this normal will be the tangent. Only thing is it should pass through point X. So we have already seen how to draw perpendicular lines in our earlier sessions of conical curves. So what I'll do is I'll go to this OSNAP features, make everything off except perpendicular. Type line command, move the cursor over to this line, it shows the perpendicular icon, and now you draw a line. Again go back to the OSNAP features, make endpoint and intersection on. We know that this is a perpendicular line, but at present it is not placed at X. So make use of move command, select this line, press enter, pick this endpoint of this line as the base point and place it at X. Then make use of extend command to extend this line on the other side. So this line is the required tangent. Select these two lines, change the color, increase the line weight. So this represents the tangent and normal. You can indicate the names. So copy any of the text and place it over here. So this is S and this is T. So this is how we construct the cycloid curve and a tangent and normal to it. Now what else is remaining as part of that question? We need to name the curve. So copy one of the texts, place it over here, double click, I am changing the text height and type this as cycloid. So we have written the name of the curve, and what else is remaining is the dimensions. So we need to show the radius of rolling circle. So type DRA, which means dim radius. Select this circle and place the dimension. The next dimension that we have to show is this distance traveled. So type DLI, which is dim linear. Pick this endpoint P and the other endpoint A and place it over here. And the next one is the distance for drawing the tangent and normal. So pick this point A and the line which is passing through X. So this shows 40 mm. So this is how we construct the cycloid curve. So I hope you have understood this. Now in the next session we will see how to construct the epicycloid curve.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.